All right, now that we've gone through a lot of hypothesis tests, let's step back and talk about the theory behind all the things we've seen. We've seen alpha. We have not seen critical value in the context of hypothesis tests. We'll talk about it now. Test statistic, we've seen. P-value, we've seen. And I'll introduce the concept of the rejection zone. So let's think back all the way to the first hypothesis test we were dealing with, and that was smelling Parkinson's. That was the activity where we were trying to see how hard it is to do what Joy Milne did in terms of smelling 12 shirts. And as a class, we were talking about how many shirts must she have correct in order for us to believe her. And different people give different numbers, but we sort of average it out and we'll say, okay, fine, 11 is good. So if she could correctly smell 11 out of 12 shirts, we'd believe her. And she ended up correctly smelling all 12 of 12. Now, as a hypothesis test, that means, first of all, we don't believe that she could smell it. So our null hypothesis is she's just guessing. If she's guessing, then her chance at each shirt is 50-50. So P is equal to 0.5. Whereas the alternative is she's doing better than just guessing. So that means P is greater than 0.5. And then we ran a simulation on what would happen if Joy was just guessing. Now let's talk about this. How significantly well must she perform for us to believe her? She must perform as good as 11 shirts out of 12. Okay, so here's the cutoff for 11, and she has to do this well. This number here, if we calculate the z-score of it, we would be calling it the critical value. The area to the right of the critical value is called alpha. And that's why I used the word significant earlier. How significantly well must she perform for us to believe her? Okay, if she performs that well, to us it's significant and we would believe her. So that's alpha. How did she do? She got 12 out of 12. So she got this, she did this well. So these are from the data. Okay, the data tell us that she performs this well, whereas the alpha and the critical value come out of the fact that before we even did anything, we sat around as a class and we decided the 11 is what we want. The significance value alpha is given straight right off the bat, and it doesn't require the data. The data will give us how well she did. And let's translate this into language we've seen. This is how significant we want Joy's performance to be. This is Joy's actual performance. If we translate the whole thing into the standardized word of z-scores, then we would have the z-curve on this side. The significance is translated to this part, and the actual data would give us the information from this part. Each of these parts has two components. It has the cutoff on the z-axis, and it has the area. This cutoff here is called the critical value, which I will abbreviate CV. And this shaded area is the alpha, is the significance level. The part that the data give us, this part here is called the test statistic. And this area is the p-value. So if you relate to a typical hypothesis testing problem, right off the bat, somewhere in the problem, it says use alpha equals 0.05. Then alpha and the critical value are something that's given right off the bat from the problem. We don't need to calculate any data. And that's the same thing with us when we were dealing with the story of Joy Milne. We sat around and we decided that it's going to be 11. By the time she got the data in and we found the 12, that's when the p-value test statistic come about. And it's consistent with how we've been calculating a hypothesis testing problem. We don't get the test statistic and p-value until after we've plugged everything into StatCrunch, and it gives us the test statistic and the p-value. So let's take a look at an example of a hypothesis testing problem. The political operative wants to test the claim that the majority of voters want a new mayor. A random survey of 200 likely voters shows that 121 want a new mayor. test at alpha equals 0.05, the operators claim. So what do we have right off the bat? We have alpha equals 0.05 right off the bat. And when is it that we get the test statistic and p-value? Not until after we've run the calculations. And we enter the data, and StatCrunch gives us the test statistic and p-value. So both the test statistic and the p-value are the result of the data, and they're tied together. So here are the relationships. First of all, the HA, the alternative hypothesis, tells us what tail is the test. In this case, if you look back, the HA has a greater than symbol, so it's a right tail test. So everything is happening on the right side of this curve. Right off the bat, we're told that alpha is equal to 0.05. So we have alpha equals 0.05. And the cutoff for alpha is called the critical value, which I will just write as CV for now. And now the p-value. The p-value we're given as 0.0015. And check this out, the p-value is compared with alpha, so it must be the same kind of animal. Alpha is an area, p-value must be an area. As a matter of fact, we know that because we know that the p-value is the probability of getting sample data at least as good as the data we got, assuming H0 is true. So p-value is also some sort of area, and the cutoff for it is the test statistic, 2.970. All right, so these are the relationship. Right off the bat, what the problem requires out of us, it's going to give us an area of alpha, and the critical value is what cuts off alpha. So critical value and alpha are both straight out of the problem, and alpha is the area of critical value and vice versa. Critical value cuts off alpha. What we compute from the data are the p-value and test statistic. And the p-value is an area, and the test statistic is what cuts it off. All right, now let me introduce the concept of rejection zone. In our example, the hypothesis is right tail. When is it that we reject H0? We reject H0 if p-value is smaller than alpha. And in terms of comparing area, if the area is over here, then it will be smaller than alpha. If the area were all the way over here, it would not be smaller than alpha. So we only reject H0 if we are falling somewhere in this area or in this portion of the axis. For p-value to be smaller than alpha, the test statistic has to be over to the right somewhere. So that part to the right of the critical value under the alpha area is called the rejection zone. So for a right tail test, that means we have our HA contains the greater than symbol. We would have an alpha that's given by the problem as an area. We would have a cutoff here that we call the critical value. And this portion is the rejection zone. If p-value is small, then it has to be in the rejection zone here, and we would reject H0. The test statistic has to be in the rejection zone to reject H0. For the left tail test, everything is on the left, alpha is on the left, critical value cuts off alpha, and the rejection zone is the part of the axis that's under alpha. For the two-tail test, it's trickier because there are now two tails, and the area has to be alpha. Well, there are two of them, so each of them is half of alpha for a total of alpha. So for the two-tail test, there are two tails with area of alpha over 2 each. The critical value is, by definition, the positive side of things. So it's the cutoff for the alpha over 2, but on the positive side, the other one is negative the critical value. All right, so let's take a look at this example. A hypothesis test with alpha equals 0.05 results in the StatCrunch output below. On the graph, mark alpha, p-value, test statistic, and critical value. You must note the numerical values except for the critical value where you only need to mark CV. So let's see, let's take a look at the StatCrunch output. We know it's a mean problem because the symbol in H0 and HA is mu. And so it's a t-test. So I'm going to mark my axis as t. I'm told that alpha is equal to 0.05. So that means I know that there's an area of 0.05 for alpha, except that this is a two-tail test. So I need half and half on two sides. So I need alpha over 2 is equal to 0.025 over here. And the other alpha over 2 is 0.025 here. If it is a one-tail test, either the right tail or left tail, I do not divide alpha. So here I have my alpha. These are areas, and it's 0.025 each. That makes this the critical value, this the negative critical value, which I don't need to fill in for a numerical value because I'm told I only need to mark CV. And now the test statistic. The data tells me that p-value is 0.1076. 0.1076 is bigger than alpha. So if it's larger than alpha, I don't draw it down here. Nope. It's bigger than alpha, I draw it bigger. Okay. Well, except there are two of them. Because again, it's a two-tail test. So I have p-value over 2 over here, and p-value divided by 2 over here as well. Here's my test statistic. Test statistic is just a number on the axis. So whatever value it is what it is. I don't divide by 2. Okay, I divide the area by 2 because I need a total area equal to certain things. Okay, the test statistic is just like the address. Test statistic is 1.616, and over here is negative 1.616. And p-value is divided by 2, so I take this p-value, I divide it by 2, I get 0.0538, 0.0538. Values on the axis can be positive or negative, depending on which side of 0 is on, but the area is always a positive number. So that's the idea. Right after I read the problem, I can write the H0 and HA. I know if the problem is right tail, left tail, or two tail, and then I draw my alpha and critical value. Test statistic and p-value come after I've run StatCrunch, and I put the test statistic and p-value in afterwards. In this case, as you can see, p-value is 0.1076, is larger than alpha, so I do not reject H0. And sure enough, if you look at the test statistic, it is outside the rejection zone. The rejection zone is here under alpha, and the test statistic is outside the rejection zone. All right, so that's how all those quantities work. And thanks for watching.